Welcome. Today we look at Chapter 2, Section B, Set Operations. In this section we'll look at universe and complement of a set, subsets, intersection and union, and Venn diagrams. Universe and complement. So every set lives within a universe, and the universe can be either implied or explicit. Here are some examples. If you see the set March, April, June, that looks like a set of months, and it looks like a bigger implied set might be the set of all months. And if you see the set containing these four numbers, 98, -1, 43, -2009, you might imagine there's some larger set that these numbers are drawn from. So the universe for the first set might be just months of the year, and the universe for the second set, well, you have some choices. Maybe it's all integers, or maybe it's all rationals, or maybe it's all reals. But by the way, the universe for this second set couldn't be natural numbers because there are some negative numbers in there. Sometimes the universe is given explicitly, like in this example. Consider the set 3, 9.8, 14 in the universe of real numbers. So there I'm just telling you explicitly what the universe is. The complement of a set is the set of all things not in the set, but inside the universe. The complement of S is denoted S prime or S with a little superscript C. You see both of these pretty often. So for example, if my set S is Monday, Tuesday, Wednesday, Thursday, Friday, and from this I infer that the universe is the set of all days of the week, then S prime, the complement of S, is the days that are left over, Saturday and Sunday. Here's an example where the universe is given explicitly. Oh, and by the way, when you see U being used to denote a set, almost always that indicates the universe. So U, the universe, is the numbers 1 through 9. And A is the set 1, 3, 4, 9. What is A prime? So A prime is the set. Everything in U that's not in A. So maybe 2, 3, 4. 5, 6, 7, 8, and then 9. Oh, that looks good. There we go. There's the complement of A. Subsets. Now, 1, 3, 5, the set 1, 3, 5 is a subset of the set 1, 2, 3, 4, 5, 6, 7, 8 because this 1 in the set is contained in the larger set. 3 appears over there, and 5 appears in the set on the right. So 1, 3, and 5 on the left all appear in various places in the set on the right. However, 1, 3, 5 is not a subset of 3, 4, 5, 6. Can you see why not? It's because of the 1. All right, 1 isn't contained in the set on the right anywhere. So in order to be a subset, every element of the guy on the left has to appear somewhere on the right. A is a subset of B if every element in A is also in B. And here's our notation for it. It's kind of like a less than or equal sign. We use less than or equal when we're comparing numbers, x less than or equal to 7. And we use this symbol when we are comparing sets and we want to show a subset relationship. True or false. Take a second if you'd like and try to remember what your different number sets are and see if these containment statements are true or not. All right. In the first example, yes, this is true. B is false. In fact, it goes the other way around. To make a true statement, it turns out that the natural numbers are contained in the rationals. C, the set 5 and 92 is a subset of the integers. That's true. And for this last one, you might have to do a little bit of work to figure out what this set is in set builder notation. This looks like the set 2, 4, 6, 8, 10, 12, 14, 16, 18. So all those even numbers that are naturals and less than 20. And I'm almost tempted to say true, except we have a 0 in there, and 0 is not in the set on the right. So no, that one doesn't work. Do you think the set 135 is a subset of the set 135? In fact, it is, because every number on the left, the 1, the 3, and the 5, they appear on the right. The 1 and the 3 and the 5. We allow this. In fact, this is another similarity with the less than or equal sign. The fact that there's that little bar kind of on the bottom indicates that, yes, you could have equal sets as well. How about these three? I'll give you a second. See if you can find any containment relationships between these three sets. All right. So for set B, let's write this out. I think it looks like just the set 1, 2. And set C, if you write it out, is really the set 1, 2, 3, 4. All the way up through 9. And, well, it looks like maybe B is contained in A, so B contained in A. And B is contained in C. B is a subset of C. But that's it. Those are the only containment relations. Let's talk about intersection and union. Let's start with an example. Consider the set A, 1, 2, 3, 4, 5, 6, and B, 2, 4, 6, 8, 10. The intersection of A and B is the set of elements that appear in both A and B. So which numbers appear in both sets? Well, there's a 2 that appears in both sets, and the 4 appears in both sets, and the 6 appears in both sets. And that's it, 2, 4, and 6. When you think of intersection, think of and. I want those elements that are in one set and the other set. How about union? The union of A and B is the set of elements that appear in either A or B. And in this case, think or, those elements that appear in one set or the other. And it's just mushing the two together. You take all the elements in both sets and you make one big set, A union B. 1, 2, 3, 4, 5, 6, 8, 10. Maybe you can remember the symbols. Don't get these mixed up. The symbol for union looks like a big U. And the symbol for intersection, well, that one's a little harder to remember. Maybe you can remember it because it's not union. Or maybe it looks a little bit like a capital A for the word and. I don't know. Maybe just remember that the first one's union. Some exercises for you to practice. So our universe, U, is the numbers 1 through 8. A is 1, 2, 3, 4. B is 3, 4, 5, 6. Take a few minutes, pause and try. Try these things, see what you can get, and then when you are ready to check your work, go ahead and start the video again. Okay, give it a try. Okay, we are back. Let's take a look at the answers. Here we go. 3, 4. 1, 2, 3, 4, 5, 6. 5, 6. 1, 2, 5, 6, 7, 8. 1, 2, 3, 4, 7, 8. 1, 2, 5, 6, 7, 8. All right. Venn diagrams. Venn diagrams are pictures that nicely illustrate set relationships. So often in a Venn diagram, the universe will be drawn as a big rectangular box that surrounds everything. And then inside of that, if you see like the circles, shaded in circles, those represent sets. So this gray area, that's my set A. And then everything outside of A, but within the universe, that's my A complement. So in this first picture, here we see the relationship between A and A complement. And just as a reminder, sometimes that A complement is written A with a superscript C. Here's an example of how we show a subset relationship in Venn diagrams. I just draw a circle B inside of a circle A, and now set B is represented as a subset of A. The intersection of two sets, well, that's kind of the area where the two sets might overlap. If it helps, maybe you think of drawing some dots throughout the area, and every dot represents a member of the different sets. So you can see every dot, there are some dots that are in set A, and there are some dots that are in set B, and we have some dots that are in set A and set B. So that area, that is the intersection of the two sets, A intersect B. It can happen that two sets don't have any elements in common. When that happens, we say that these sets are disjoint. Incidentally, if two sets are disjoint, then it turns out that A intersect B equals the empty set. And there's actually a funny conclusion that we can draw from this. When I take the intersection of two sets, the result is a set of elements that are contained in both of the sets. So this empty set is a subset of A, and the empty set is a subset of B. In general, it just turns out the empty set is a subset of every set. It's a little bit weird, but maybe here's our justification by thinking about disjoint sets. The empty set is a subset of every set. Here's an example that shows the union of A and B, the idea that both A and B are shaded in. So everything that's in either A or B. How would you shade the area represented by A union B intersect C? Now, parentheses are important. If you see some sets that are grouped with parentheses, do that first. So what does A union B look like? Let me shade all of A union B. There we go, something like that. There's A union B, but I want to intersect that with C. So the intersect is and. What do they have in common? Which elements are in A union B and in C? And it looks like that will be just this area right here. So maybe I'll erase everything else. There we go, and we're just left with this region. A union B intersect C. One more example. How about A complement intersect B union C? Yeah, pause the video if you'd like to try it on your own first or think about it for a second. All right, and then we'll take a look at the solution. Here we go. A complement, so everything not in A. Well, I don't have my big universe box. I guess I could draw it if I'd like. But for the A complement, think of everything outside of A. Maybe I'll draw my shading like this. Now, it looks a little bit messy, but everything outside of A, that needs to get intersected with B union C. Can you see what B union C looks like? B union C are these two circles together. B union C right there. So what is the intersection of everything not in A together with those things in B union C? And I guess it looks like this. There we go. I really shaded it in to emphasize it. All right, so there's A complement intersect B union C. And that brings us to the end of section 2B on set operations.